Well, good morning. I'm delighted to be here and give a talk. I'm Emilia Koch. I'm a PhD student at the University of Hohenheim. And we looked into scoring data and how to model it according to its structure. And a biologically intuitive way to do this was the hurdle model. So let's start with scoring data.
Emilia, sorry, this control room. Can you stand in the middle of the podium, please? Because you're actually being recorded. If you stand in the middle of the podium, that's fine. If you stay there, please. The mics can pick you up as well. You're off camera otherwise.
Thank you. Okay. Oh, I'm louder. So we have soybean leaves here. So imagine we have a soybean trial for diseases, and we have something going on. We want to evaluate it and model it. And we would use a scoring scheme. So we do have ordinal data. A scoring scheme is like we give ordinal scores. And this is an example scheme for the sake of this presentation. But so it has the commonality of all scoring schemes that we use, that the first score is a point score, whereas all the other scores are a range. Why do we do this? Well, it's simple. And sometimes it's like it would be hard to estimate a precise score, and it could be compared to interval-censored data where we see, as examples here, well, we go every morning, see what is infected, what is dead, but we don't know exactly the time. We can estimate it only. So how do we model this? We could use ANOVAs. ANOVAs are used a lot. They can implement a lot of designs, but we do have ordinal data. It's not normal, it's not metric. And for ordinal data, we would use something maybe like the threshold model. The threshold model was developed for ordinal data. However, it does estimate the thresholds. It does estimate our classes, but also the thresholds. And in our case, we do know the thresholds. We do not need to estimate them. And if we would plot this, it would more look like this. And we already see we don't have a range for the first class. We do have a point score. And the ranges are given. So looking at closer the data, we could see how the hurdle model works or how the idea is. So we do see, is it infected with the point score or not? And how much is infected? And exactly that is what the hurdle model does in 2 steps. So we have 2 parts in our model. First part and second part, but it's both parts in one model. The first part looks at it in the sense of like, is it healthy or is it not healthy? And the second part then looks at it in a sense of like, how healthy is it? Only taking the diseased part of the data. So we have a closer look at this now to see how we did that. We start with the first part. The first part is a binomial part. Is the disease there or not? And to model this, we define a linear predictor. Our linear predictor tells us an expected value. It consists of an intercept, a location effect, treatment effect, and a random interaction. Once we have the expected value, we can estimate the probability. We have here inverse logit function, and here's our expected value. And we have our first part, the probability for our observation being diseased. Now, when we look at the second part, we pass the hurdle of 0% and only look at the diseased data. We would do an intermediate step before we go to modeling. We transform our data. Precisely, we don't transform our data. We do transform the thresholds because we know the thresholds, so it's good to use them. The thresholds are transformed according to Johnson SB. The theory of Johnson SB simply says we take a value, we transform it according to this formula, and we get a value that is that is normally distributed. If we do this with our thresholds, we get them normally distributed. So we can picture this a little bit like it's laying on the normal distribution, and here we already see why we exclude the 0. It would lay at minus infinity. The advantage, as our previous speaker said, of like having something we know is we can use models we know here. So the area underneath the normal distribution is the probability. But before we go there, we have our transformation. Now we need our linear predictor. There are multiple options. We explored multiple options. One way would be to say that our second linear predictor is a linear combination of the first one. It's very suitable because it's very parsimonious. We only have to estimate one set of parameters plus 2. This is a strong assumption, so we also explored what is if it's not the case. So we have 2 complete set of parameters that needs to be estimated. We can fit covariance, because the assumption of them being strictly independent is very strong, and if they're strictly independent, we could as well do like 2 separate models. We wouldn't need to do the hurdle model that does both in one model. And we can test what is most suitable. So we have our linear predictors, and we estimate a probability for each class here as the area underneath the distribution. We use the threshold model for this. Feel free to ask me about these formulas. But now we have the probabilities for each class. We estimated them. Here's a binary distribution. Here is a multinomial distribution. And similar to other models, we now need a likelihood. If we take the logarithm, they're additive. So we do have 2 likelihoods functions that get additive if we take the logarithm, which combines both linear predictors into one model. This is the model. So what do we get out of it? We heard earlier that it's kind of nice to have a biologically relevant, like a model that shows something about the biology. As we have 2 linear predictors, we also get 2 results, 2 sets of parameters, 2 sets of results, 2 significance values, 2 sets of estimates, variance components, but they answer different questions. The first part about disease incidence, which we heard is very important, answer as well, is the disease present? In the case of plants, we could see if there's a difference in the first part. In the presence of disease, we could see, well, maybe there's a thicker cuticula that inhibits the entrance of the fungus. If we see differences in the disease severity, so there's different amount of disease present, we could probably or eventually have a hypersensitive response. As soon as the fungus enters the cell, it dies, and we have a programmed cell death. So it may give us an idea where we need to look at the underlying processes. So in this sense, it's a nice model, it's a nice concept. It gives us ideas of what's the biology behind it, or it can explain or show, okay, there's the biology that we assume behind it. It can account for an excess of zeros, which is often present in disease data. This part is very flexible. We can fit different kinds of models here. We do not need the threshold model. There can be different kinds of distributions. It's still in a very early stage. There's no package yet, but we look forward to developing it further. So with this, I want to thank Professor Pifo and Professor Hartung, who's not here, for their support and supervision, and I'm open to questions.